Hi, everybody. Welcome back. So we've finished our study of solutions all while learning from home, if you can believe it. And today I'm going to help us review, hopefully, by going over some of the homework problems that the most people missed throughout this unit. So you can follow along as I show you how I would solve all of the most missed problems. So here we go. Our aim is 8.8, review solutions. I'll walk us through the question of the day, then I'll do all the most missed homework problems from the whole unit of solutions. And then homework 18 is a review as well. So you can try your hand at that. Pretend it's like a test, see how it goes for you. And then we'll go over that on Thursday before you take your real test. All right, so today's question of the day: which pair of substances would dissolve well in each other? So this question gets to the concept of like dissolves like, or in other words, in order for you to have a good solution, there has to be an attraction between the particles, between the solute and the solvent. So in other words, there has to be an intermolecular force. So if the substances are similar, then they'll have similar intermolecular forces and they'll dissolve each other really well. When we're talking similar, we're thinking, are the substances polar, nonpolar, or ionic? If they're polar and nonpolar, they don't go together. But if they're polar and ionic, they'll go great together. Or if they're both nonpolar, they'll go great together. If they're both polar, they'll go great together, etc. All right, so this first one is H2O and CH4. Now, if you draw those out, you can look at their symmetry, and you would see that water is not symmetrical, while CH4 is. So that means water is polar, CH4 is nonpolar. Those would not make a good solution. How about the other option? Oops. H2O and CaF2. Well, H2O we just said is polar. CaF2 is a metal and a nonmetal, so that means it's ionic. So water and an ionic substance do go great together, something polar and something ionic, and that would make an ion-dipole intermolecular force. So that would make a great solution. Like salt in water, dissolves really well. The second question was, which intermolecular force would make this possible? That's the ion-dipole force. And then the last question is to draw an atomic level diagram of this solution. So let me draw that right now. Right here, right now. I got to put in a screen for it. I'll put it in right here. What would that look like? All right, so we know it's Ca and F are in the compound, and water is the solvent. So write that here, H2O and CaF2. All right, this is ionic, so it'll break apart into ions. It'll be positive calcium and negative fluorine. And I got those charges from looking at the periodic table. And then the water is polar. Do you guys remember which end of the water is a little bit more negative? Yeah, that's right, the O side. So I'll put a little, oops, put a little, that means a little bit negative. And then the hydrogen side is a little bit positive. There we go. The O side is more negative because oxygen has higher electronegativity. All right, so when this dissolves, the positive ion, calcium, what's going to be attracted to that? The negative or the positive? Well, the negative. So that means it'll get surrounded by water molecules with the oxygen side towards the calcium. Here's a little Mickey Mouse, oops, Mickey Mouse water molecules. And then the fluorine will be opposite. Here's my little negative fluorine, it'll be surrounded by the positive side of all the water molecules. And those ion dipole attractions, oop, oop, I drew these water molecules smaller for some reason, not sure why. The ion dipole attractions will form between the polar molecule and the ion, and again between the polar molecule and the ion. So that's what the solution would look like. All right, so here's some answers to homework 17. I'll just go over a couple of them. Number 2 said, how does adding a solute affect a substance's boiling point? Well, boiling points are elevated, freezing points are depressed when you add a solute. So a boiling point would be increased if you add a solute. I'm going to get to 4 later in this lesson, so I'll skip it for now. 5B, explain why shop owners throw salt on their sidewalks, and then why would it be more efficient for them to use calcium chloride than sodium chloride? In our last lesson, we saw that if something makes more ions when it dissolves, it has more of an effect. And calcium chloride splits apart into calcium positive and 2 chloride ions, whereas sodium chloride splits apart just into sodium and chloride. So this guy makes more ions. It makes 1, 2, 3 ions. This one only makes 2. So it has more of an effect on the freezing point. Number 6, explain the trend shown in the graph below. Here we've got on the x-axis the molarity of a sucrose solution. Sucrose is a kind of sugar. So this means the molarity of the sugar solution gets higher and higher and higher as you go this way. And the y-axis is the normal freezing point. So we can see for pure water, it was 0 degrees Celsius. That's when there was 0 sugar in it, just water. And then when it was a 2 molar solution, it looks like the freezing point went down to -4 degrees Celsius. When it was 4 molar solution, it went down to about -8, etc. The more the moles of solute added, the lower and lower and lower the solution would have to be before it would freeze. That's an example of freezing point depression. And then this one asks, which one has a lower vapor pressure? Vapor pressure is the pressure exerted by a gas that has evaporated from a liquid. So here's a pure substance. Here's a solute added. So this one will be harder to boil, or in other words, boiling point elevation. It'll take more energy before it's boiling. So that means it's going to exert less vapor pressure if they're at the same temperature, because less of the particles will have evaporated. Fewer of the particles will have evaporated. All right, announcement. We have our first distance learning test. It will be on Thursday. You'll have from Thursday to Sunday to finish it. What will the test be like, you might be wondering? It's going to be open note. So you can use any notes you've taken. And that means you can also use your reference tables, calculators. You can use the PowerPoints I've provided. It's going to be on GoFormative, so very similar to your homework. And you'll have from the end of class Thursday until Sunday to complete it. Here's some things you can study to get yourself ready. The homeworks that we've done since we started distance learning, so that's number 10 through 17, those are all on GoFormative. Any notes that start with an 8, if you've taken any notes from any of these PowerPoints, you can use those. Look back through each PowerPoint might be a great idea, or the video, or both. And then also the review homework you're going to do tonight is going to be very similar to your test. All right, so our aim is 8.8. How do we solve the most missed homework problems that were about solutions? All right, from homework 10, Intro to Solutions, this was the most missed question. An aqueous solution of copper sulfate is poured into a filter paper cone. What passes through the filter paper? So if we think about our definition of a solution, we said you cannot filter it. That means if you tried to use a filter and you poured the solution, the whole thing would go through the filter, because the holes in the filter are not small enough to be able to differentiate between the solute and the solvent, because to be a solution, the solute has to be dissolved down to the molecular or ionic level, and no filter is going to be small enough to be able to catch that. So the answer to this one is, since you cannot filter a solution, the whole thing would just go through the filter. Then if you had a solution of copper sulfate, the whole thing would go through, both the solvent and the solute. All right, this was the most missed question from homework number 11, solubility. It was a question that said, for each potential solution below, write whether or not you think it would make a good solution. If so, and here's the key, write the name of the intermolecular force that would attract the solute and solvent. If not, write why not. And I offered a hint that if you don't know if something is polar or not, you could try drawing a Lewis dot diagram or looking it up to see if you can tell if it's symmetrical. So this part, the name of the intermolecular force, we learned about 3 types: weak intermolecular force, dipole force, or hydrogen bond. So those are you're looking for one of those 3 if it's going to be a solution. So let's take a look at our solute and our solvent. We want to think, if they're going to make a good solution, we're thinking, okay, does like dissolve like? Are these substances alike in terms of their intermolecular forces? So this is CH3OH, this first guy, methanol. This is H2O, water. Looking at them, do they look symmetrical? No, symmetrical this way, but not the other way, right? And this one isn't symmetrical anyway. So if they're not symmetrical, that means they are polar. And both of them are polar. So they are alike, and like dissolves like. So yes, they will be soluble. Now we want to think, which type of intermolecular force would attract them? Well, if they're both polar, then it could be a dipole-dipole force. Now you'll notice they're both superpolar and they both have a FON atom in them and hydrogen atoms. So that means they could be attracted with a super strong dipole force called a hydrogen bond. So either of those would be a right answer for this one: dipole-dipole or hydrogen bond. Hydrogen bond is probably a little better. Okay. For homework 12, factors affecting solubility. For this one, it asked us to use table G to answer the following questions about solubility. How many grams of HCl can be dissolved in 100 grams of water at 50 degrees Celsius? So let's take a look at table G, the solubility curve. So we're looking at HCl, which is this curve. And it said, how many grams can be dissolved in 100 grams of water? That's everything on that chart is 100 grams of water at 50 degrees Celsius. So yeah, here's our 100 grams of water. So let's look at 50 degrees Celsius. So here's 50. We follow that up to here and then look to the left. It looks like about 58 grams-ish of solute at that temperature of HCl. All right, the next one that was missed a lot on homework number 12 were 9 and 10. It said, a solution is made by completely dissolving 90 grams of potassium nitrate solid in 100 grams of water in a beaker. The temperature of the solution is 65 degrees Celsius. Question 9 said, describe the effect on solubility of potassium nitrate solid in the solution when the pressure on the solution increases. So we know that pressure can affect solubility. That's why soda is kept under high pressure, right? To keep the carbon dioxide gas bubbles soluble in the soda. But potassium nitrate solid is not a gas, it's a solid. So pressure has no effect on a solid. Number 10 said, determine the total mass of potassium nitrate solid that settles to the bottom of the beaker when the original solution is cooled to 15 degrees Celsius. All right, well, let's take a look at the solubility curve again to solve this one. So we've got 90 grams of potassium nitrate. It's being cooled down to 15 degrees Celsius. Okay, so there's the curve roughly for potassium nitrate. And as we can see, first there were 90 grams of potassium nitrate that was all dissolved. So that was an unsaturated solution. But then the solution was cooled down to 15 degrees Celsius. Whoa, so if all of that had stayed dissolved, if they'd been very careful about it, that would have been a super saturated solution. But at 15 degrees Celsius, the saturation point for potassium nitrate looks like is about 28 grams, right? Like right about there. So the solution cannot hold all that 90 grams anymore. This would be a very supersaturated solution if they managed to, keep it all in there. But most likely the solute will fall out. So how much will fall out of solution and sink to the bottom? Well, it'll be the difference between 90 grams and 28 grams. So if you just subtract those, I thought I put the answer in here. Oh yeah, 68 grams. So yeah, 90 grams here is how much originally was in there, but then it'll go back down to the saturation point at 28 grams. So about 68 grams, the difference here, will just sink to the bottom and be sitting at the bottom of the beaker. All right, from homework 13, saturation and solubility. Here were the most missed problems. An unsaturated solution is made by completely dissolving 20 grams of sodium nitrate in 100 grams of water at 20 degrees Celsius. This was a review question, A. It said, show a correct setup for calculating the number of moles of sodium nitrate. They even told you the gram formula mass. Isn't that nice? So you don't have to figure it out for yourself. Used to make this unsaturated solution. So this is just remembering from our study of stoichiometry, how do you go from grams to moles? So we start with the given, put it here in the top left, and then got a unit that has to go, you put that unit down below, so the gram formula mass goes down here, and then 1 mole goes at the top. And you don't even need an answer. For this one, you just can show the setup. For part B, it said determine the minimum mass of sodium nitrate that must be added to this unsaturated solution in order to make it a saturated solution. So we've got 20 grams of NaNO3. Let's see if it's already saturated. Let's look at table G. So here's the curve for NaNO3. They said the solution was at 20 degrees Celsius and that there was 20 grams. So is this solution saturated right now? No, not at all. You'd need to put in a lot more for it to be up here at this line and be saturated. So the question is, how much more? Well, it looks like the saturation point for sodium nitrate at that temperature is about 88 degrees, 88 grams of solute. We put in 20 grams already, but we want 88 grams total. So 88 minus 20, that means we'd have to add about 68 grams for this to be saturated. All right, I also included a most missed question from the mini lab, hot ice, which was about supersaturation. So this is the most missed question. It said, at the end of step 5, is the solution unsaturated, saturated, or supersaturated? So here's a reminder of the procedures from the mini lab so you can tell what the question is about. So you goggle up, you put 5 grams of sodium acetate in a test tube, then you add some water, then you heat it slowly. Then when it's all warm and dissolved, you add two more crystals, and then you stir till dissolved. So the fact that you're able to dissolve all of this, and it's very warm, remember, so it can hold a lot of solute because it's pretty hot, and you're stirring it, it's all dissolving. If everything is dissolving, that means you could probably dissolve more at that temperature, right? So that means it is unsaturated. It can still fit more. From homework 14, molarity, the topmost question was number 6. How many liters of a 5.6 molar solution do you need if you have to have 4.3 moles of solute? So this is just a rearrangement of the molarity equation, which is molarity equals moles over liters. You can rearrange that and say, well, liters equals moles over molarity, because they said, how many liters do you need? Here's the molarity, and here's the moles. So liters equal moles per molarity. So 4.3 over 5.6 equals 0.767857, etc. On your calculator would say a bunch. But if we just use 2 sig figs for our answer, because there's 2 here and 2 here, then the answer would be 0.77 liters. All right. From homework 15, percent by mass volume in parts per million, the most missed question was number 6. What is the percent by mass of a saturated solution of potassium chlorate at 20 degrees Celsius? And the hint says to use your reference table G. Okay, so percent by mass, we know an equation for that. The hint there is that it's a saturated solution. So that will tell us what we need to use the percent by mass equation, because the percent by mass equation, which as a reminder is on the back of your reference tables here, is grams of solute over grams of solution times 100%. Okay, so if we look at potassium chlorate on the reference table, this curve is a little off, but you can see what I was going for here. And we look at saturated it, let's remind ourselves the temperature, 20 degrees Celsius, okay. So here's 20 degrees Celsius. So saturated would be right here. Let's look to the left. It looks like that would be approximately 8 grams of potassium chlorate. Now you might be wondering, but how much solution is that? Well, we know that's in 100 grams of water. But remember, the solution includes not just the solvent, but also the solute. So you'd want to say 100 grams plus the 8 grams of solute to find the mass of the whole solution. So here's the equation again. Mass of part over mass of whole times 100%. So 8 grams of solute in 100 grams of water. The mass of the whole is 108 grams. The mass of the part is 8. So 8 over 108 times 100% is about 7.4% by mass. All right, from homework 16, people did a really great job on this homework, but the top missed question about vapor pressure and boiling points was number 5. What is the vapor pressure of ethanoic acid at 55 degrees Celsius? This question, we can just look on reference table H, which is the vapor pressure of 4 liquids. So they asked us about ethanoic acid at 55 degrees Celsius. What would be its vapor pressure? Okay, so we'll look at ethanoic acid. There's the curve. And then they told us it was 55 degrees Celsius. So take a look at that temperature, and then we look to the right to look at the pressure there. And notice something a little funny about this graph. These lines on the x-axis go up 5, 10, 15, 20, 25, whereas the lines on the y-axis go up 10, 20, 30, 40, 50. So they go up by 10s on the y-axis, but 5s on the x-axis. So I think that might be why some people got this wrong. So at 55 degrees Celsius, it's about 10 kilopascals of pressure, vapor pressure. All right, and then from our last homework, homework 17, colligative properties, this question 4 said, which aqueous solution of potassium iodide freezes at the lowest temperature? So this question is about boiling point elevation, freezing point depression, specifically freezing point depression. So we know that the freezing point of a solution is lower than the freezing point of pure water, freezing point depression. We know that the more solute you add, the lower the freezing point will go. So that means that whichever of these solutions has the highest concentration of particles will freeze at the lowest temperature. You can kind of think of it like this. What would be harder to freeze? A little teacup of salt water or a whole swimming pool of salt water? Right? A whole swimming pool would be harder to freeze. So it's not just like how many moles of salt they put in there, but also how much water is there, because that determines the concentration, right? So here we see that here's only 1 mole in those two solutions. These ones both have 2 mole, but this one is 2 mole and only 500 grams of water. This is 2 mole of potassium iodide in 1,000 grams of water. So number 2 will be more concentrated, higher concentration of the solute because there's less water there. So that means that that one will freeze at the lowest temperature. It will be most affected by the 2 moles of salt, of potassium iodide. Okay. For this last mini lab quick freeze, everyone who's done it so far has gotten 100% of the questions right. So I didn't pick one from there, but you could go back and look over the mini lab to remind yourself how it worked. All right, so great work, you guys. Tonight's homework is to do homework 18 on Go Formative, which is the review for Unit 8 exam solutions. And you'll notice that this review also contains a little bit of info from the previous units. That's just because as we get closer to the end of the year, I like to try to incorporate a little bit of review before we're studying for our finals. So you'll notice a little bit of review in there too. But the test will be mostly on just Unit 8 solution stuff. All right, best of luck. Let me know if you have questions. Great work, you guys. Bye.